Bismillahirrahmanirrahim. Hi everyone. I hope you are all doing well. My name is Azmat Ali and I welcome you all in class of Elementary Number Theory by David M. Burton. In today's lecture we will discuss problems 2.2 completely inshallah. So let us start from question number 1. The question number 1 says prove that if A and B are two integers where B is positive, then there exist a unique integers q and r satisfying a is equal to bq plus r, where r is the remainder that lies between 2b and 3b. Actually, this is the modified form of standard algorithm. In the standard division algorithm, you can see when you write a is equal to bq plus r, then your remainder always lies between the numbers 0 and b. But in this question you can see that it can be possible, it is possible that your r can lies between any other interval other than 0 and b, like here r lies between 2b and 3b. So let us prove this. By standard deviation algorithm we can find unique integer q naught and r naught such that you can write a is equal to bq naught plus r naught, where r naught lies between 0 and b. We further can write it as by adding and subtracting the number 2b here. By combining the terms bq naught with 2b minus 2b and r naught plus 2b. By taking b common factor from this bracket, we have a is equal to b times q naught minus 2 plus r naught plus 2b. As q naught, b and r naught are the integers, and the difference of two integer is always an integer, as well as sum of two integer is integer, so q naught minus 2 and r naught plus 2b also an integer. So let us say that q naught minus 2 is another integer q and r naught plus 2b is equal to r. This implies your a becomes a is equal to bq plus r. This shows that the form exists. Next we show that our remainder lies between the interval 2b and 3b. As we have supposed that remainder r naught lies between 0 and b, so by adding 2b in each part we have 0 plus 2b, r naught plus 2b, b plus 2b. This becomes 0 plus 2b plus 2b, and r naught plus 2b is equal to r, we have supposed here. So we can replace r naught plus 2b with r, and b plus 2b is equal to 3b, which is required. Further you can see here actually what is the author purpose in asking this question. To show flexibility in the division algorithm, the standard form is not the only possibility. You can have a different intervals for the remainder r, provided you are careful to adjust the algorithm. For example, if you take a is equal to 17 and b is equal to 5, then standard division algorithm, then according to standard division algorithm, you can write 17 is equal to 3 into 5 plus 2. So here q naught is 3, that is the quotient, and remainder is 2, which is always less than b. But in the modified division algorithm, you can write it as 17 is equal to 1 into 5 plus 12. So here the quotient is q is equal to 1, dividend is 5, and your remainder is r is equal to 12. And you can check that your remainder lies between the interval 2b, which is equal to 10, and 3b, which is equal to 15. Next, in the question number 2, uh, we have to any integer show that any integer of the form 6k plus 5 is also of the form 3j plus 2, but not conversely. In this question, we have to show if an integer has the form 6k plus 5, then it can also be written as in the form 3j plus 2, but its converse is not true. So let us suppose that there is an integer n that have the form 6k plus 5 for some k belong to z. We can write it as, we can write 5 is equal to 3 plus 2 by taking 3 as a common factor from this bracket. We have 3 into 2k plus 1 plus 2. As k is an integer, so clearly 2k plus 1 is also an integer. So let 2k plus 1 is another integer j. So we can replace this 2k plus 1 with j. So we have n is equal to 3j plus 2. Hence, n can be converted into another form 3j plus 2. This shows that every integer of the form 6k plus 5 is also of the form 3j plus 2. Now to prove conversely, we will give a counter example. We take j is equal to 0 here. We put j is equal to 0 here. We have n is equal to 2. Now we try to express 2 in the form of 6k plus 5. So take 6k plus 5 is equal to 2 and find k from here. We find k is equal to minus 1 by 2, which is not an integer. So 2 cannot be written in the form of 6k plus 5. So not every number of the form 3j plus 2 is of the form 6k plus 5. Actually, what does this question say? In other words, this question can be expressed as, if an integer leaves the remainder 5 when it is divided by 6, then on division by 3, it must leave the remainder 2. But if an integer leaves the remainder 2 when we divide it by 3, then it is not possible always that it will must give the remainder 5 on division by 6. Question number 3. Use a division algorithm, establish the following. The square of any integer is either of the form 3k or 3k plus 1. This question says, if you have any integer a, then its square is always of the form 3k or 3k plus 1. Let a be an integer. We need to show that its square is either of the form 3k or 3k plus 1. So when we divide a by 3, then the possible remainders are 0, 1, 2. When r is equal to 0, then a is exactly of the form exactly multiple of 3, and hence a is equal to 3q. Suppose my a is 5. When you divide 5 by 3, the remainder is 2. Suppose my a is 6. When you divide 6 by 3, I have a remainder 0. Similarly, if a is 3 and we divide 3 by 4 by 3, we have remainder 1. So the possible remainder are 0, 1, 2. Now, when your remainder is 0, it means your number integer a is always exactly multiple of 3. When your remainder is 1 and 2, it shows that number is not exactly multiple by 3. So a number which is exactly multiple by 3 can be written as 3 into q. So when your remainder r is 0, then a is exactly multiple of 3, and hence it can be it has the form of a is equal to 3q. Similarly, when your remainder r is equal to 1, then a has the form 3q plus 1. For r is equal to 2, a is equal to 3k plus 2. Now we show that in each case, square of a is either of the form 3k or 3k plus 1. Okay. My first case is when a is equal to 3q. Taking square, we have a square is equal to 9q square. That can be written as 3 into 3q. As q is an integer, so 3q is also an integer, so we replace 3q is equal to k. So this becomes 3k, where 3q is equal to k. This shows that a square has the form 3k. When a is equal to 3q plus 1, by taking square on both sides, we have this form 9q square plus 1 plus 6q. By combining these two terms and taking 3 as a common factor from this bracket, we have 3 into 3q square plus 2q plus 1. As q is an integer and sum of two integer is always an integer, so 3q square plus 2q is also an integer, so we suppose this is equal to k. Hence a square is equal to 3k plus 1. Similarly, when your a is 3q plus 2, by taking square and after some algebraic manipulation, you can write a square is equal to 3k plus 1. Hence, this shows that your a square is either of the form 3k or 3k plus 1. Next in question number 3b. We have to show that the cube of an integer has one of the form 9k, 9k plus 1, 9k plus 8. I am just sharing the solution of this question, and I hope you can understand the solution very easily, because if I elaborate each question, the length of the video will increase significantly. So you can see the solution very easily. Next, I am discussing question number 3c. The fourth power of any integer is either of the form 5k or 5k plus 1. When we divide an integer by 5, because now we have to prove the integer has the form 5k or 5k plus 1, so we will divide the integer by 5. So when we divide the integer by 5, then your remainder will always lies between 0 and 5. So the possible remainders are 0, 1, 2, 3, 4. Let a is equal to 5q plus r, and by putting different values of r, we have different values of a. When r is 0, your a is 5q. Now we have to prove its fourth power. So by taking its fourth power, a4, which gives 5 times q whole power 4, that is 625 q4, which can be written as 5 into 125 q4. As q is an integer, so its any power is also an integer. As integral so its power 4 is also an integer. So let us say this is an integer k. Hence a raised to power 4 is 5 times k. When your remainder r is 1, then your a is 5q plus 1, by putting r is equal to 1 here. By taking power 4 and by using binomial theorem, we have the form 625 q4 plus 500 q cube, 150 q square plus 20 q plus 1. By taking 5 as a common from the first 5 terms, we have 5 into this plus 1. Say this is an integer k, so it is equal to 5k plus 1. Similarly, when you take your remainder r is 2, your a is 5q plus 2. Taking power 4, we have again 5k plus 1, where k is now this. Similarly, we can discuss other cases when your remainder is r3 and 4. Hence, in either case, a raised to power 4 is of the form 5k or 5k plus 1. Next, question number 4. This is a very nice question. In this question, we have to prove 3a square minus 1 is never a perfect square. You can take any a here. 3a square is never a perfect square. For example, if you take a is equal to 1 here, your number is 3 into 1 square minus 1, which is equal to 2, and 2 is never a perfect square. Similarly, if you take integer a is equal to 2, this gives 3 into 2 square minus 1. 2 square 4, 4 3 is 12, 12 minus 1 11, 11 is not a perfect square. So for any integer a, 3a square minus 1 is never a perfect square. We will prove this question we suppose that for some integer n, we can write it as, we prove this question on the contrary. Suppose there is an integer n such that 3a square minus 1 is a perfect square and it is equal to n square. From question number 3a, the square of any integer is either of the form 3k or 3k plus 1. So case number 1, if n square is equal to 3k, in question number 3, we have proved that the square of any integer has a form 3k or 3k plus 1, as we have claimed that this number is equal to the square of this integer n. So we suppose if n square is equal to 3k, if n square has a 3k form, this becomes 3a square minus 1 is equal to 3k by putting n square is equal to 3k in star. This equation can be written as 3a square minus 3k is equal to 1 by taking 3 common from these two terms. This can be written as 3 into a square minus 1 is equal to k minus k is equal to 1. By Division algorithm, we can write 1 as 3 into 0 plus 1. If we compare these two equations, we have a square minus k is equal to 0. But this is not possible, because if a square minus k is equal to 0, this shows a square is equal to k. Then star becomes 3k minus 1 is equal to 3k, because if you put here a square is equal to k, as if a square is equal to k, and whenever you put here a square is equal to k and n square is equal to 3k, this equation becomes 3k minus 1 is equal to 3k, or this implies minus 1 is equal to 0. By subtracting 3k on both sides, this gives minus 1 is equal to 0. This is impossible. So case number 1 is not valid. If n square is equal to 3k plus 1, this implies 3a square minus 1 is equal to 3k plus 1. We can write it as, by subtracting 3k on both sides, 3a square minus 3k is equal to 2. By taking 3 common, we have 3 into a square minus k is equal to 2. By Division algorithm, the number 2 can be written as 3 into 0 plus 2. So again, same conclusion can be drawn as in case number 1, because here again a square minus k is equal to 0 by comparing these two equations. Hence, in both cases are not valid, and hence 3a square minus 1 is never a perfect square. Question number 5 is a very easy question. In this question, we have to show that for any integer n greater than or equal to 1, this number n into n plus 1 2n plus 1 6 over 6 is an integer. You can see that here the quotient, here the denominator is 6. So by doing algorithm, when we divide an integer n by 6, then it has of the form n is equal to 6k plus r, where r is 0 1 2 up to 5, because here the quotient is 6. So we will consider the case this, when we divide n by 6, it will give the remainder less than 6. So the possible remainders are 0 1 2 3, and n has the form 6k plus r. Okay, when your r is 0, then your n is equal to 6k. So put n is equal to 6k here. This becomes 6k plus 1. When you put here 6k, this becomes 12k plus 1 over 6. By cancelling out 6 in the numerator and in the denominator, this gives k into 6k plus 1, 12k plus 1. As k is an integer, so this number is also an integer. Hence, for r is equal to 0, this number is an integer. Next, when your r is equal to 1, then your n has the form 6k plus 1. So when we put n is equal to 6k plus 1 here, We have 6k plus 1, 6k plus 2, 12k plus 3. By cancelling out 6, by taking 3 as a common multiple from this bracket and taking 2 common from this bracket, we have 6 into 6k plus 1, 3k plus 1, 4k plus. Cancelling out 6, we have 6k plus 1, 6k plus 3k plus 1, 4k plus 1. That is again an integer. Similarly, we can check for all other cases when your n is 6k plus 2, 6k plus 3, 6k plus 4, 6k plus 5. This number is always an integer. Show that the cube of an integer is of the form 7k or 7k plus minus 1. Let a be any integer. When we divide a by 7, it leaves the remainder 0, 1, 2 up to 6. So a has one of the form a is equal to 7q plus r. This form you can obtain by division algorithm, where your remainder r is 0 less than or equal to r less than 6. Now we check in all cases your cube is always of the form 7k, 7k plus minus 1. So when your r is 0, your a becomes 7q. Its cube is 7q whole cube, which can be written as 7 into 7 square q. As 7 square q is an integer, because q is an integer, so this becomes, say this is k, so this becomes 7k. Similarly, when your r is 1, then your a becomes 7q plus 1. By taking cube on both sides, we have, by expanding the cube and taking 7 as a common multiple from the first 3 terms, we have 7 into this. Say this is equal to integer k, this becomes 7k plus 1 form. When your remainder r is 2, we have a is equal to 7q plus 2. By taking cube on both sides and after expanding cube, considering the first 3 terms and taking 7 as a common, we have this form, and say this is equal to k. Similarly, this has the form 7k plus 1. When your r is 3, your a is 7q plus 3. Now when you expand its cube, this gives us 3 whole cube. The last term is 3 cube, that is 27. We can write it as 28 minus 1. So by taking 7 as a common from these 4 terms, so this has the form 7k minus 1. By taking this number is equal to some integer k. Similarly, we can check that for remainder r is equal to 4, 5, 6. Hence, in each case, a cube has a form 7k or 7k plus minus 1. Question number 7. Yes, this is an interesting question and little bit difficult. Obtain the following version of division algorithm. This is also another form of division algorithm. This question says that for integers a and b, where b is non-zero, there exists a unique integer q and r satisfying the equation a is equal to bq plus r. Now your r lies between these two intervals in the absolute form. It is given that b is non-zero. If b is non-zero, it means b is either positive or b is negative. But in any case, your absolute value b absolute is positive. So division algorithm hold, because division algorithm says that if your divisor b is positive, then there exists a unique integer q and r such that we can write a is equal to bq plus r. So if here b absolute is positive, so division algorithm hold and there exists a unique integer r dash and q dash such that we can write a is equal to b times q dash plus r, where your remainder lies now 0 less than or equal to r dash less than b absolute. Okay, as b absolute is positive, so we can break the interval 0 less than half b absolute and half b less than b absolute into two parts. The half of any positive value, suppose here b is b absolute, this will always less than b absolute, and the absolute is always positive. So we have this interval. I can break this interval in two parts. In the first part I can write 0 less than half b absolute, and in the second I can write half b absolute less than b absolute. Now the two cases are possible. Either our remainder r dash is greater than b absolute, half of b absolute, or it is possible that r dash is less than half b absolute. Case number 1, I have to prove there are I have two targets to prove. One, I have to prove this form, and other I have to prove that my remainder is always lies in these two values. So I am considering the first case. If r dash, that is the new remainder that I have set here, if r dash lies, if r dash is less than half of b absolute, but it will always greater than or equal to 0. So for this remainder r dash, if I set r is equal to r dash, because r dash is a arbitrary remainder value, suppose this is r and my quotient q dash is equal to some q, so then star becomes, what is star? Star is this is my star. A is equal to uh, bq dash plus r dash, where r dash is this. If I set here r is equal to r dash and q dash is equal to q, I can achieve this form: a is equal to bq plus r. A is equal to bq plus r, where my r dash is lies between 0 less than 0 and half of b absolute. Case number 2, in the case if r dash is greater than half of b absolute, then half of b absolute is less than r dash, but r dash is less than b absolute. By subtracting the number b absolute in each part, we have minus half b absolute less than r dash minus b absolute less than 0, by subtracting b absolute from each part. As we have supposed a is equal to bq dash plus r dash, this number can be written as, by adding and subtracting b absolute, and suppose this is my equation number double star. Now here there are two cases. If my b is greater than or equal to 0, then clearly b absolute is equal to b by definition of absolute value. So I replace this b absolute is equal to b and combine these two terms to make the form, to make this form r dash minus b absolute. So replace b absolute is equal to b, and by combining these two terms we have a is equal to bq dash plus r dash minus b absolute plus b. By taking b common from these two terms, I have b into q dash plus 1 and plus r dash minus b absolute. As q dash is an integer, so q dash plus 1 is also integer. Suppose this is equal to q and r dash minus b absolute is equal to r. So again I have the form a is equal to bq plus r, where r dash lies between minus half of b less than r dash and r dash less than r dash minus b absolute less than 0. Case if when b is negative, then b absolute is equal to minus b. So now star becomes, this is my star, double star, sorry, a is equal to bq dash plus r dash minus b absolute plus b absolute. So writing this b absolute is equal to minus b and combining these two terms as it is r dash minus b absolute. So by combining bq dash with minus b and taking b as a common, as q dash is an integer, so q dash minus 1 is also an integer. Say this is equal to q and this is equal to r. I have a is equal to bq plus r, where minus half of b absolute less than r dash minus b absolute less than 0. So by combining both of the cases, I have A is equal to BQ plus R when minus half of B absolute less than R is less than half of B absolute. Okay, and it completes the proof. Next, question number 8 is also an interesting question. We will discuss this question. We will discuss this question by two way. In this question, we have to show that there is a no integer in the sequence 11, triple one, tetra one, penta one, up to so on, which is a perfect square. None of the number is a perfect square in this sequence. The first method is I can choose any typical term of the sequence, and you can observe that we can write that term in the form of 4k plus 3. For example, consider the number triple one, 111. You can write it as 108 plus 3. 108 you can write it as 4 into 27 plus 3. Suppose this 27 is equal to some integer k plus 3. So this number triple one can be written as 4k plus 3. Similarly, any number in the sequence you can write it as 4k plus 3. For example, the first number 11, you can write it as 4 to the 8 plus 3. So any typical term of the sequence can be written as 1 1 1 1 up to some 1 1. The last three ones can be written as 1 1 1 1 0 8 plus 3. That is 4k plus 3. Now we show that 4k plus 3 is never a perfect square. I have to show that any number in the sequence is not a perfect square. So I have started this question in such a way that I have chosen any typical number in the sequence, and I claim that that number has a form 4k plus 3, and this number is never a perfect square. Okay. In other words, we show that there is a no integer n such that 4k plus 3 is equal to n square. Or we can say that 4k is equal to n square minus 3, or more simply we can say that k is equal to 4 divides n square minus 3 and gives some integer k. So finally we show that n square minus 3 is never divisible by 4. 4k plus 3 is never a perfect square is equivalent to show that this number n square minus 3 is never divisible by 4. We use induction to prove this. Let us suppose that the statement is denoted by Pn, which is equal to n square minus 3, where n is greater than or equal to 2. For n is equal to 2, we have 2 square minus 3, which is equal to 1. This shows that 4 does not divide. This vertical line shows divisibility, divides. And this shows no divides. This shows 4 does not divide 1. Suppose that the statement is true for n is equal to s, where s is an integer. It means 4 does not divide s square minus 3. This implies there does not exist an integer q such that s square minus 3 is equal to 4q. So s square minus 3 is not a multiple of 4. That is, s square minus 3 does not equal to 4q. Next we show that next we check the statement for n is equal to s plus 1. So consider the number s plus 1 whole square minus 3. Actually, I have to show that 4 does not divide n square minus 3 for any integer. So when you put n is equal to s plus 1 here, this becomes s plus 1 square minus 3. So we solve this number s plus 1 square minus 3. By expanding square, we have s square plus 1 plus 2s minus 3. Combining s square with 3, we have s square minus 3 plus 2s plus 1. As by the hypothesis, we supposed s square minus 3 is not divisible by 4, or s square minus 3 is not a multiple of 4. And 2s plus 1 is always an odd integer which is not divisible by 4. As the sum of 2, as this number s square minus 3 is not divisible by 2, as well as 2s plus 1 is also not divisible by 2. So this is not possible that the sum of two number is divisible by 4. Hence, uh, 4 does not divide s plus 1 square minus 3. This implies 4 does not divide n square minus 3 for all n belong to Z. And this shows that hence none of the number in the sequence is a perfect square. Alternatively, we can prove this question by logics. In the logics, uh, if you have some little knowledge of discrete mathematics, in the discrete mathematics, you know, in logics, an implication and its contrapositive are always logical equivalent. Uh, we have a necessary condition: a perfect square is always of the form 4k or 4k plus 1. As each number in the given sequence has the form 4k plus 3, so it cannot be a perfect square, and it ends the proof. Note: here we are using contrapositive of the statement. Suppose my statement is P, which says if a number is a perfect square, then Q, it is always of the form 4k or 4k plus 1. This is my implication: P implies Q. It's contrapositive. Negation Q implies negation Q, where negation Q is it is not of the form 4k or 4k plus 1. Negation P, it cannot be a perfect square. So, this shows that if it is not of the form 4k or 4k plus 1, then it cannot be a perfect square. That we have done in this question. As the number has the form 4k plus 3, that is not of the form 4k or 4k plus 1, so it cannot be a perfect square. Question number 9. Question number 9 is also an interesting question, and it also needs some correction. In the question, we have to show that if an integer is simultaneously a square and a cube, such that in the case with 64 can be written as 8 square plus or also can be written as 4 cube. So 64 is a square as well as a cube of an integer, of two integers. Then it must be that it has either of the form 7k or 7k plus 1. Okay. Suppose that the required integer is n. That can be written as the square and the cube. Square of t and cube of m for some t and m. When we divide m by 7, then by division algorithm, the remainder is 0, 1, 2, 3 up to so on 6. Firstly, we show that the cube of this integer has the form 7k or 7k plus 1. In the question number 6, we have shown that the cube of an integer is always of the form 7k or 7k plus 1, which gives the required result. You can write the solution of question number 6 here. In the question number 6, we have shown that the cube of an integer is always of the form 7k and 7k plus 1. I have supposed when we divide m by 7, then m has the form by division algorithm, m is equal to 7k plus 1. When you put r is equal to 0, your m is 7q. Its cube is 7 into 7 square q, which is equal to 7k clearly. Similarly, when you put r is equal to 1 here, you can again have m is equal to 7q plus 1. When you take m cube, it will again have the form 7k plus 1. So in each case, when you put here r, you can find an m, and its cube is always of the form 7k plus 1, and finally your n is have the form 7k plus 1 because m cube is equal to n. Next. Okay, next in case of square, when n is equal to t square. Now we show that this number integer n, which is a square as well as a cube of another integer at the same time, is of the form 7k, 7k plus 1, and it also has the form 7k plus 4. So this is the correction that is needed in this question. So let my integer t is 7q plus r form, where my remainder is lies between 0 and 7. When r is equal to 0, your t becomes 7q, and its square is 7 into 7q square. Sorry, 7 into 7q square. Right, this is equal to k, this is equal to 7k, this becomes 7k, and your t square becomes 7k, and finally you can say that your n, because t square is equal to n here, your n is equal to 7k. Similarly, when your remainder r is 1, then your t becomes now 7q plus 1. By putting r is equal to 1 here, by taking square on both sides, and after expanding square, and with after some algebraic manipulation, we can write it as t square is equal to 7k plus 1, where my k is now this. Again, this is equal to n, hence n has the form 7k plus 1. When your remainder r is 2, by taking square of this number, and after some algebraic calculation, we have t square is equal to 7k plus 4. Now, when you taking square on both sides, and after expanding square, we have 49q square plus 4 plus 28q. By combining these two terms, we have 49q square plus 28q plus 4. By taking 7 from these two terms, this becomes 7 into 7q square plus 4q plus 4. So this is the form of 7k plus 4, not of the form 7k plus 1. So in this case, your n has the form, another form 7k plus 4. When your r is 3, now my number t is 7q plus 3. So when you will take square, now I have the form of 7k plus 2. Similarly, when you take r is equal to 4, after taking square and after some calculation, now I reach at 7k plus 2 again. Similarly, when your remainder r is 5, now you have the form 7k plus 4. When your r is 6, again you have a form 7k plus 1. So the square of an integer, when it is divisible by divided by 7, has either of the form 7k, 7k plus 1, 7k plus 4, 7k plus 2. Question number 10. For an integer greater than or equal to 1, establish that this integer is of the form 7, 6q. Because now I have to prove the form in 6k. So by division algorithm, if we divide n by 6, it has the form n is equal to 6k dash plus r. You can write it as n is equal to 6q plus r if you are irritating with k dash. So where your r lies between, 0 and 6. So by putting different values of r, we have different values of n. The first value of n is 6k dash. So putting n is equal to 6k dash here, I have 6 into k dash plus 252 k dash square plus 5. After some calculation, by setting this number is equal to k, we have 6k. Similarly, when you put r is equal to 1, now your number is n is equal to 6k dash plus 1. By putting this number in here, n, by replacing n is equal to 6k dash plus 1, we can write it as, and after some calculation, I have again 6k plus 6k form. When your r is 2, now your n is 6k dash plus 2. By putting this value of n here, and after some calculation, I can reach at 6k. Similarly, for other remainders, we can show that each time this number has the form 6k. The last question, question number 11. If n is an odd integer, show that this number n raised to power 4 plus 4n square plus 11 is always of the form 16k. Let my n is 4k dash plus 1 form. Then if I replace n is equal to 4k dash plus 1 form, this becomes 4k dash plus 1 whole power 4. 4 into 4k dash plus 1 whole square plus 11. By taking expanding power 4 by using binomial theorem, I have these 5 terms. By taking square, I have these 3 terms plus 11. Collecting the like terms, we have by taking 16 as a common, we can write it as 16 to this as k dash is an integer, so sum of 2 or more than 2 integer is always an integer. So say this is equal to k, which is required. In this question, there is no need to write n as the form n is equal to 16 cube plus r, where r is lies between 0 and 16. Because when you choose here n is equal to 4k dash plus 1, this form is always gives the final form of 16k. So I hope now you have a clear understanding of problems 2.2